AI with the right maps ensures that the algorithm can accurately analyze subsurface and surface conditions to predict optimal locations for new development wells. Below is a comprehensive list of maps that are commonly used in AI models for well location optimization. 1. Subsurface maps. These maps are critical for understanding the geological and petrophysical characteristics of the reservoir. Structural maps show the geometry of subsurface formations and fault lines. Examples: top reservoir structure maps, fault plane maps. Isopack maps indicate the thickness of specific reservoir layers. Porosity maps represent the distribution of porosity across the reservoir. Permeability maps highlight areas of high and low fluid flow potential. Water saturation maps help in identifying hydrocarbon-rich zones. Seismic attribute maps include amplitude, coherence, and other seismic features that indicate reservoir properties. Pressure maps show reservoir pressure distribution for understanding drainage and reservoir connectivity. Gas thickness map.jpg. This map indicates gas cap thickness in the reservoir based on log curves recorded after a certain injection period. For infill drilling locations, thick gas area, red on the map, has to be avoided. 2. Production and operational maps. These maps provide historical data and operational constraints. Production rate maps indicate areas with high and low production rates from existing wells. Cumulative production maps show total hydrocarbon recovery, identifying depleted and untapped areas. Injection maps highlight zones of water or gas injection in enhanced recovery operations. Drainage maps illustrate areas influenced by existing wells to avoid interference. Water production.jpg. This bubble map indicates monthly water production. Larger the bubble, riskier the drilling, production, and has to be avoided. 3. Surface maps and 3D displays. Surface maps address logistical, environmental, and infrastructure constraints. Topographic maps provide elevation data for site accessibility and surface facility planning. Land use maps show land ownership, environmental restrictions, and surface rights. Infrastructure maps include roads, pipelines, and facilities for planning drilling operations. 3D displays include properties, fault and juxtapositions, other well location in reservoir that needs to be analyzed for planning drilling operations. Fault 3D view.jpg. 4. Economic and risk maps. These maps assist in integrating economic and risk factors into AI models. Cost maps highlight areas with varying costs for drilling and operations based on terrain and infrastructure. Risk maps indicate geological risks such as fault reactivation, water breakthrough, or unstable formations. 5. Hybrid and derived maps. Derived maps integrate multiple datasets to provide composite insights. Reservoir quality maps combine porosity, permeability, and saturation data into a single indicator of reservoir potential. Hydrocarbon probability maps generated using AI, showing the likelihood of finding hydrocarbons in undeveloped areas. Sweet spot maps indicate zones with optimal reservoir properties and minimal operational risks. Cross-section well trajectory and model.jpg. Any suggested location has to be checked vertically. Geological model can be used to analyze property distribution. 6. Temporal and dynamic maps. Temporal data helps in understanding changes in the reservoir over time. 4D seismic maps monitor changes in the reservoir caused by production or injection. Pressure depletion maps track reservoir pressure reduction over time. Integration of maps into AI models to optimize their use. These maps can be georeferenced, standardized spatial alignment for AI analysis. Layered in GIS platforms, overlay maps to visualize interactions between geological, operational, and surface factors. Converted to numerical data, use grid-based formats or voxel data for AI ingestion. Model 3D view.jpg. Selecting infill drilling locations using AI involves a combination of data analysis, machine learning, and reservoir simulation. Here's a general approach: data preparation and analysis. Gather historical data. Collect relevant data on existing wells, including production rates, pressures, reservoir properties, and well locations. Data cleaning and preprocessing. Clean the data to remove inconsistencies and errors, and preprocess it to make it suitable for machine learning algorithms. Feature engineering. Create relevant features from the data, such as well spacing, reservoir pressure gradients, and production decline rates. Machine learning model development. Choose a suitable algorithm. Select a machine learning algorithm appropriate for the problem, such as classification, to categorize well locations based on their potential for infill drilling success. Regression. To predict production performance at potential infill locations. Clustering. To group similar wells and identify areas with similar reservoir characteristics. Train the model. Train the chosen algorithm on the prepared data to learn patterns and relationships. Model evaluation. Evaluate the model's performance using appropriate metrics, such as accuracy, precision, recall, and F1 score.